Sorry. Sometimes I forget to hit the record button. I was just recording everything and it was like filling up my hard drive. Okay. I was trying to be more selective. But does that make sense?
Mm-hmm.
So number 25, we used the Moivre-Laplace limit theorem to do it, but we had to do the continuity correction. We had to adjust that thing up by a half unit. And using the Poisson, and that does a really good job. It does a better job than approximating by the Poisson. So yeah, there we go. All right, what else? Other questions?
Can we talk about problem 16?
16.
Mm-hmm.
Annual rainfall in a certain region is normally distributed with mean 40 and standard deviation 4. What is the probability that starting with this year, it will take more than 10 years before a year occurs having a rainfall of more than 50 inches? Okay. It seems like there might be a couple of distributions floating around here.
Yeah.
So it seems like what you're going to do in a given year, in a certain region, the annual, so in a year, the rainfall is normally distributed with mean 40 and standard deviation 4. More than 50 inches, for more than 50 inches. Okay, yes. So it looks like, I think we're going to combine a couple of different distributions. You're first going to compute the probability that that happens, that you have more than 50 inches, right?
Mm-hmm.
And then what you're going to do is you're going to say, all right, every year I'm going to do this experiment. Does that make sense? The experiment is in a given year, did I get more than 50 inches of rainfall or not? Does that make sense?
Mm-hmm.
So it's a Bernoulli trial. Okay, you're executing that Bernoulli trial, and it has a certain probability that comes from the normal distribution.
Mm-hmm.
And you're waiting that it will take more than 10 years. Oh, okay, so I'm just waiting for the first time that that happens or something.
Right. Mm-hmm.
So what distribution is that?
Seemed like it should just be, I'm gonna get this wrong. I wanted to say some sort of binomial. Like,
Binomial, it's you're waiting for the first success?
no, wait.
Okay, let's just kind of try to set this up.
A negative binomial?
Well, of some kind, a version of the negative binomial.
Oh, is this just geometric?
Yeah.
Okay.
So let's say that X is distributed as normal with mean. So what was the mean? The mean was 40.
Yeah.
And the variance. Well, okay, so I'll just say this. I'll say sigma. Sigma is 4, yes?
Mm-hmm.
And I want to know the probability. I want to know the probability that what? We get more than
50.
50?
Yeah. Mm-hmm.
Okay. And I can compute that.
Mm-hmm.
David, do you want to? So in Excel, it would be. Is it? How do they say it? Is it normal? Normal.s.dist.
I don't think you can use standard normal on this one.
Oh, right. But that, yeah, right.
Because I got the first part where you found the normal. I don't remember if I still have that up.
You could use the standard normal if you went like this. If you said this is the same as the probability that x minus 40 over 4 is greater than 50 minus 40 over 4,
Mm,
right? This right here, that's like, you know, the standard normal.
right.
The normal with mean 0 and standard deviation 1. Okay, so that's the probability that z is greater than, what's 10 over 4? Is that like 2.5?
Yeah.
By the way, doesn't that make sense? Think about that for a second. When we subtract the mean and divide by the standard deviation, we just get a standard deviation of 1. So every 1 unit for the z random variable, every 1 unit is 1 standard deviation. So basically asking for the probability that x is bigger than 50 is the same as asking what's the probability that x is 2.5 standard deviations above the mean, right? Does that make sense?
Mm-hmm.
Because think about it. Okay, man, I keep doing that. I'm sitting here for 10 seconds pushing my finger on my screen up here, and that's not the thing I should be pushing, okay? So watch, if you go z, right, z is equal to x minus mu, correct?
Mm-hmm.
So what does that mean that x is equal to? What's x equal to? Mu plus z sigma. So basically what the z is measuring is it's simply measuring how many standard deviations above or below the mean am I? If z is equal to 1, that means that x is 1 standard deviation above the mean. If z is equal to 0, that means that x is right on the mean. Does that make sense? If z is equal to minus 1, that means you're 1 standard deviation below. So z is equal to the number of standard deviations above or below mu that x is. Okay, and above, right, how would I tell if it's above? Well, it would be plus. And how would I tell if it's below? Well, it would be negative. That's how we would know. Okay. So back over here, and back over here, it makes sense that when we translate the probability that x is bigger than 50 to the standard normal, you say to yourself, well, 1 standard deviation is 4 units. So I'm basically asking for the probability that x is 2.5 standard deviations above the mean. Yeah? And that is exactly reflected in this probability related to z. Yes? It's because we see, okay, that's the probability that z is bigger than 2.5. Z is literally the number of standard deviations above or below the mean we are. Okay? So what is that probability? Now you can actually look that up, right? So that's, that would be equal to 1 minus, you could look it up in the book if you wanted, or, so this would be 1 minus phi of what? Of 2.5. Okay, so what's that?
0.00621.
0.00, oh, oops. Oh, man. 0.00621.
I think so.
Okay, but that's not the end of the problem. What we wanted to know, okay, so 0.00621 is the probability that in a given year, we have more than 50 inches of rainfall, yes?
Mm-hmm.
Then we make another random variable, okay? By the way, let's call this probability P, right? So, right, so this is the probability of success. success for us is going to mean that we have gotten more than 50 inches of rainfall in a given year. Is this making sense so far? You all right? Emma, are you okay so far?
Yeah. I'd done it a different way. At least I thought. I just used. Anyway, I did it a different way, and I got the same answer as the back of the book, but I'm unsure about.
Okay, we're still not done, right? So I mean,
Yeah.
we can kind of. So then let's let y be distributed as geometric with proportion of success. What was our proportion of success? Right?
Mhm.
What are they asking us? They want the probability that what?
It takes more than 10 inches. I mean, it takes more than 10 years.
Yeah, and what, okay, and they ask us before we even do that, what assumptions are we going to make about given years?
They're independent?
Yeah, that they're independent, like each one of those trials is independent. So that's one of the assumptions we're making. So it'd be the probability that y is greater than, I guess more than means strictly greater than, right?
Mhm.
More than 10, which is 1 minus the probability that y is less than or equal to 10. Yeah? And then we could probably use Excel. Okay, yeah, so let me do that. And I think Excel, it's a little bit screwy. Like they don't actually have the geometric singled out in Excel. Like if I go equals 1 minus, it doesn't what I'm, oh man, it has the hypergeometric, but it doesn't have the geometric. You know what I mean? So what do you think I should use?
The binomial. With one.
Binomial? Which
negative.
binomial, David?
The negative binomial.
Yeah,
With like
yeah.
1 as the number of successes.
Yeah, the negative binomial. That's exactly right. Negative binomial. Number of failures. Oh man. So like here we have to put our thinking caps on. So y was less than or equal to 10, right? And that would mean that there was a success on the 10th one. Yes? Does that make sense? That there was a success on the 10th one. Because after all, remember what we wanted was, we wanted 1 minus the probability that y was less than or equal to 10, correct? And that and y equal to 10, right? We have to think about this. Y equal to 10 would mean that we had success on the 10th trial, which means how many failures was there?
9.
9.
Yeah, it's easy to screw that up. Okay, so negative binomial, number of failures, 9. What's our number of successes?
1.
Okay, and if we really wanted to be super accurate, we could go normal. I could even put that probability in here, you know what I mean? Like normal standard distribution, or what was it? 1 minus normal standard distribution. What was this thing? Normal standard distribution of,
2.5, I think.
was it 2.5?
Yeah.
Mhm.
Okay. Cumulative. Yeah. You've entered too few arguments. What are you talking about?
I think you need to tell it that you want the normal standard to also be cumulative.
Oh, okay, yeah. Okay. Is that the answer?
Yeah, that's right.
Yeah.
Okay. Does that make sense? They were kind of putting you through the ringer, trying to make sure that you could kind of merge all these different distributions together.
Yeah, I'm just confused, I think, because it works out to the same at the back of the book, but the back of the book just has the original answer we found from the standard normal, the 0.9938 to the 10. And I just having trouble connecting that back with the geometric, I guess.
Well, that's also true, because yeah, right, because of this. Oh, that's sweet. So watch this. Oh man, let me share this again. Wait, what am I doing? Come on. Okay, let me see here. Okay, share screen. Do this. Okay, so watch this. Yes. So watch this. I think you'll enjoy this. And I think we've done this before, but it's always good to remind ourselves of these things. So if I have an X that's like geometric with, oh man, with proportion of success, P, okay?
Mm-hmm.
What is the probability that X is greater than or equal to little x? Well, what's the probability that X is equal to little x? It would be Q to the X minus 1 times P. Yeah?
Right. Mm-hmm.
That would mean X minus 1 failures followed by a success. What would the next thing be? Well, if if capital X is equal to little x plus 1, that would mean we had X failures and then a success, correct?
Right.
Q to the X times P. And do you see the pattern? What's the next one going to be?
Q to the X plus 1 times P.
All right. We've played this game before, I think. Okay, so this is like Q to the X minus 1 times P. Pull that out. That's going to be 1. Okay, here we go.
Okay.
1 plus what?
Q plus Q squared. Okay.
And what is that?
Q to the X minus 1 times P times 1 over 1 minus Q.
Right.
Okay.
If this is 1 over 1 minus Q, what's that? What's 1 over 1 minus Q?
Oh, 1 over P.
That's just 1 over P.
Okay.
So then this just ends up being Q to the X minus 1.
Okay. So that's where we're getting that Q to the 10, because we're really solving for X is greater than or equal to 11.
Yeah.
Okay.
So all right. So this. So back to this one. This is the same thing as the probability that what?
Y is greater than or equal to 11.
Greater than or equal to 11, which we just showed, right? We don't even need Excel anymore. Which we just showed is going to be Q to the X minus 1.
Mm-hmm.
Is that right? So
Yeah.
it's going to be 1 minus P raised to the 10th.
Okay.
Which is that what they have in the back of the book?
Yeah.
Mhm.
Yeah. Hey. That's pretty cool. So by the way, this is, just so that you're aware, that means that we just take the probability that X is greater than, what was it? X is greater than 50. Is that what that was?
Mm.
Mhm.
And you raise that to the 10th power.
Okay. Yeah.
What was X? X was the normal distribution, right? So X was distributed as normal with mean 40 and standard deviation 4.
Hmm.
Yeah. Oh, I mean, I like this stuff. You guys might disagree, but I think it's pretty cool. So, yeah. You guys have some other questions?
I did. I was working on number 17.
Okay.
Next one down. And it looks like you need to find the mean and the standard deviation. And I found the mean all right because you're just using like symmetry because it's like you have a bell curve basically with all these salaries. But I was a little confused about how we're supposed to go about finding the standard deviation. I'm assuming that we're using like the standard normal instead of just normal distribution.
Okay, salaries of physicians in a certain, that's the one you're talking about?
Yeah,
Salaries of physicians in a certain specialty are approximately normally distributed. If 25% of these physicians earn less than 180,000 and 25% earn more than 320,000, approximate what fraction earn blah. Okay. All right. What do you guys think? Any ideas? Hmm. Any ideas?
Sorry, what problem is this?
Number 17.
17. All right.
So
Well,
I thought we could probably just use like Excel with what you were doing in class or on your videos, but we first have to find what the mean is and the standard deviation in order to use that. Is that kind of where we should be going or not at all?
okay, yeah. So, right, but don't you know some stuff here? So first of all, how did you figure out what the mean was?
That was just going to be like the 3,200,000 plus the 1,800,000 divided by 2.
Right, it's just right in the middle.
Yeah.
Since you have 25% on either side,
Yeah.
the curve has to look like here. I'll sort of draw a picture here. Okay, so I mean, what you know here is, okay, here's this bell-shaped curve like this, right?
Mm-hmm.
And what you know is that there's 25% basically, 0.25 here, and there's 0.25 there, okay? And you know that the upper one is like 320. Okay, let's just say, let's forget about the thousands, okay? 20. And then 180. Yeah. So wouldn't you, so the right in the middle, you know that you would have 250 or something, right? Is that what,
Mhm.
250,000? And your only question is, hey, what in the world is the, what in the world is the, you know, what value corresponds? Well, look, let's kind of transform this. Oh man, I drew an arrow that's too big. Let me erase this. Why don't we just transform this into the Z realm? Okay. What's right in the middle of the Z?
0.
0. That's right. And you know that that 320 is going to correspond to something down here. Yeah. 320 is going to correspond to some kind of value. Let's call it Z, little z sub 0.25. Okay. And that just means that there's 25% down here. Can you figure that out? Can you figure out a little z value where that happens? Can you sort that out? What is that little z sub 0.25 going to be? Sorry, this iPad is connected to my wife's phone, so she's always getting all these weird texts from friends. But yeah, so so what would I do here? What's z sub 0.25? How would I find that? Wouldn't I just use Excel or the back of the book or something? Yeah.
Yeah, you're just going to do the inverse of the standard normal, right?
Yes. Okay. So so a place that has 25% above it has how much below it?
0.75?
0.75. So it'd be equal to normal, standard, inverse, and you would have to deliver the probability that sits below this thing, and I get that. 0.67449. That makes sense? 0.67449. But you know that you have this formula that like z is equal to, z is equal to x minus the mean, or mu, divided by sigma, right? Okay. And what we know is that 300, okay, so what z value did we get here? 0.67449 is equal to, well, that's what we got when we translated 320 down, right? That was what we got when we did 320 minus what? What was the mean we found?
250.
250 divided by sigma. So do you see that you can solve for sigma now?
Mm-hmm.
What's sigma going to be? Sigma is just going to be equal to 320 minus 250 divided by this thing. But that's supposed to be in thousands. Do you know what I'm saying?
Mm-hmm.
So it's 103,000. So it should be 103,782. Is that what's in the back of the book?
Well, that's not what we're looking for yet.
But now you have it, right?
Yes. Mm-hmm.
And so
Okay.
you can just do all the computation by using that.
Yep.
Does my rationale make sense here?
Right. So then what we had to do was go and transform it into like the standard normal. Is that what you're doing?
Yeah, I just transformed everything into the standard normal. Actually, Excel doesn't require that at all. It has all, I mean, you could do all of the computation. Now that I have the mean and the mean and the standard deviation,
Mm-hmm.
I mean, if you look in here, it goes normal distribution. Look, the normal distribution, you can hand in the mean and the standard deviation and do all the computation without converting to the standard normal if you really wanted to. Okay. But I mean, it's kind of good practice to know how to go back and forth between a normal and the standard normal, because that's where you put all the data on the same equal footing.
Okay.
Does that kind of help? Does that help?
Yeah. Mm-hmm.
So less than 200, for instance, 200,000. So you go 200,000, comma, what's the mean? What was the mean?
250. Or
250,000. Okay, and what's the standard deviation? Apparently,
103,782.
yeah. And I want the thing to be cumulative, right?
Mhm.
They said less than 200,000, right? So I go like that. Is that the answer?
I can't. Oh, yes.
31.498.
Yep, that's what they wanted.
Okay. So we got it. All right. You guys good for now? Hey, don't forget to turn in your test. That's like due today, right? Okay. Well, we'll have some kind of homework quiz probably next week, but not this week.
Okay.
I think we're going to be finished with chapter 5 in short order. We'll go on to chapter 6 and do some joint distribution stuff. And I think we'll probably get to the central limit theorem, which will be a nice way to conclude the course. So yeah. But I think right now you probably should have most of the stuff you need for the P exam. I think you should have most of it. But I mean, you will probably joint distributions are fairly helpful, I guess. So we'll cover that though, and then you should be in really, really good shape. Okay. Anything else, or is that it? All right. Hang in there. I'll see you guys. I'll see you soon.
Thanks, Dr. Hammett.
All
Thank
right.
you.
Yeah, thank you.
See ya.